Hello, good day. Greetings to everyone, and thank you very much for the invitation. I'm going to share this brief presentation with you. Well, the main idea of my presentation is the use of exploring experimental machine learning in film restoration. That is to say, what machine learning is in the field of film restoration. First, I will outline how the presentation will proceed. We will discuss what machine learning is, why we should create our own models, color restoration, spatial restoration, gauge and generation restoration, and restoration with analog video references. What is machine learning? Broadly speaking, machine learning is a subdiscipline of artificial intelligence. Within the vast world of artificial intelligence, a subset is machine learning. The idea is that it learns patterns from data sets, and it will apply that knowledge it has learned, that inference it has learned, to new data. For instance, as you can see in this image here, we will be using a certain number of frames to train. For example, you can use 40 frames to train a shot that is, say, 500 frames or something like that. Now, why should we create our own models? For example, there are commercial or rather general models like Runway, Firefly, Mishar, Nestable, and Fusion. You are familiar with the different names, which are trained on massive datasets typically created for new content. With the exception of, I believe, Runway and a couple of others that now can also create image by image. They are not designed for the specific challenges of film restoration. For the most part, they are not designed for that. They are designed for modern material. General models run the risk of homogenizing the unique qualities of each film. Usually, when a film is processed through these general models, it comes out quite plastic, very, very sharp. It is a very particular aesthetic that films have when they are processed through these general models. And obviously, a very important part is that using copyrighted data in training raises legal concerns. Most of these models are trained with proprietary data. They haven't necessarily obtained the correct permissions. Instead, they are general data, gathered as much information as possible without asking anyone, and trained with that to create those models. In the end, some applications might actually be useful and others might not. And my final idea is that we should advocate for small, focused models that run locally on our own machines to address specific film-related issues. The first part I'll talk about is color recovery with reference. We will address the fading of dyes and color degradation in chromogenic films. Films, for instance, that use the Eastman color, Fuji color, and Africa color processes, among others. We will use a color reference such as a DVD, a telecine, or any reference that has the intact color, since it had already been lost in the film, to extract the color information. And it doesn't matter if that reference has compression or resolution issues, that can be somewhat fixed. We are going to train a small machine learning model with X number of frames or N number of frames adapted to the complexity of the footage. And the more complex the movement, the more complex the footage, we will use a greater number of frames. And we will replicate the color throughout the sequences. This can work in a shot, in a sequence, or in a full reel. The first thing I want to show you is this example I did with Candy Candy. As you can see here, the original film came in this condition. A film that had lost almost all its color. So we had a DVD. I was given a DVD. This DVD had full color characteristics. Obviously, if you compare the DVD with the 16 millimeter film, the size is different. To a certain extent, there's some warping, even the subtitles in Japanese, so it's a different kind of DVD. So you can't just perform a compositing operation and pull the chroma, and that's it. It needs to be trained so that the machine learning model we create can fill in those gaps and differences. Here I have a complete example. The first time I tried to do it for the entire reel. Here you can see that I trained 33 images from the DVD, 33 images from the 16 millimeter. It works partially. I would say it's not a very satisfactory result. But then, for example, if we do it shot by shot, look at the much more specific, simpler model, mainly due to the complexity of the animation. 4 frames from the DVD, 4 frames from the 16 millimeters of the film, we can create a much more satisfactory result. For example, this would be the original, and this is the version that has been restored. if we compare them side by side, we can see the significant difference. It's the same film in the same 16 millimeter size with the same resolution, but we have restored the color. That's the idea. Now, I'm going to show you how this finished film looks. You can see in the upper left corner, this is the original film, how it came magenta, red, blue, partially degraded as it's called. Had a lot of flicker. The magenta, obviously, on the left, on the top right, is the clean version. Balanced, the channels have already been adjusted to remove that reddish tint. In the lower left is the DVD, which we've used as a color reference, and in the lower right is the result of machine learning 2. Nothing has been lost. The full frame has been used and recovered. So the idea behind this is, let's move on to the next example. What happens when there is no color reference? For instance, it's the last copy of a faded or magenta film. This often happens in Latin America because we often kept the exhibition positive as a last resort, and the exhibition positive was already degraded. Distribution print, and the distribution print was already degraded. So there was no color reference. We can use similar images such as paintings, photos, or other parts of the same film to infer the color. Colors by training with complete color data, or we can paint keyframes in Photoshop as you see there. The idea is that if you don't have a reference, you can create your own reference. Now, when you create your own reference, you are somewhat entering the realm of drawing. You're somewhat venturing into the reinterpretation of the archive as you're intervening in it. So it slightly steps out of the restoration range. But the example I'm going to show you is quite interesting. This is a short film called The Rebellion of the Tops, made with many paintings. Paintings by different painters from the Peruvian Viceroyalty. So here, you can see it's with voiceover, but basically they are paintings by Pancho Figueroa, Rugendas, among others. And here you can see it's with voiceover, but basically they are paintings by Pancho Figueroa, Rugendas, among others, which is a sequence. The cameraman moved the camera, making them interpret. It's not so much animation, but rather a sequence of images with certain camera movements. And the idea was, for example, if we have this short film made with these images, and obviously we no longer have the color reference because it's the last remaining copy, we can use the original images, like any paintings that can be found. So I set out to search on the internet for all the paintings I could find. So here we have all the paintings I could find from the film and more. Because the idea is that with so much variety of films as well as of artists, the idea is that when we don't have a reference, when we don't have the complete reference and want to infer, for example, the other details, I can use, for example, a similar painting or artwork to give me colors that the artist or the kind of stroke the artist uses to complete filling in that the color information. So here we have, for example, an approximation of how it would be. This is the finished color version, and this is the original. Let's see. Here, one interesting thing I had to do here was that there was a whole set of images that were in black and white, which you obviously have to include in the training to tell the machine, these images that are in this color, don't touch them, leave them in black and white. I only want you to recover that color from the images that have been from the streets. So it's also part of the learning process to tell it what it needs to learn and what it doesn't. I think it's very important to do this, and it will show us the complete demo. You can see the film is very magenta and badly damaged. It needs to be cleaned first. Part of every machine learning process is that preliminary cleaning and care process to ensure all machine learning procedures are successful. There must be a preparation of the material, dataset preparation, or training material preparation. That is very important. You can see here there is a lot of variety in images, and moreover, the panning and tilting movements are respected. Now we will move on to the next point, which is spatial restoration with reference. We aim to restore the lost spatial details of films caused by damage or generation loss, whether, for example, due to a copied film or simply damage to a film, whatever it may be. Use a secondary reference, whether telecine, a different copy, or an alternate copy, to build a machine learning model that retrieves the original spatial features of the film. We are going to use three techniques. One will be gauge recovery, that is from 16 to 35, or from 8 to 16, or from 8 to 35, generation recovery, and recovery of analog video references. Train the small row in 16 to acquire the characteristics of the 35 row. Or for example, if we have 4 rows in internegative and 1 row in positive, we can train that positive row with overlapping to train the model so that the positive has the characteristics of the internegative. And subsequently, we will align the quality of the film with the best available source. The idea is to homogenize it to the best available source. Acquire the characteristic of the 35mm reel, or for example, we have 4 reels in internegative and 1 reel in positive. We can train that positive reel with the overlay, so we can train that model for the positive to have the characteristics of the internegative. And in this way, subsequently, we are going to align the quality of the film with the best available source. The idea is to homogenize it to the best available source, and the best match of visual characteristics ensures a cohesive appearance among the different source materials so that everything is homogeneous. Let's start with this demo of Mission Kill, a Hong Kong film. Great. The idea was that we had the 16mm film, which was, well, actually, it's not that damaged, but it was noticeable that unlike the 35mm, it had a significant change in definition. For example, if we show the faces, we have one face here and another face here. There was a significant change in definition. I don't want you to notice the color. Obviously, what had happened was that the internegative had already turned magenta. But if we look only at the brightness, there's a huge difference between them. The details in the internegative are much larger. In the 35mm internegative, they are obviously much larger than in the 16mm positive. So the idea is that we can also train the 16mm film to have the definition and characteristics of the 35mm internegative. Here we have them. The result, for example, this is the original 16, and this is the 35, and this is the training that has been done to 35. What will happen here is that at times there is a bit of noise, which indicates that more training needs to be done. For the sake of speed, I did everything together in one scene due to the complexity of the scenes and the movement, because it is a movie that includes, for example, martial arts and all that. Due to the complexity of the scene, this should be done shot by shot, but for convenience, I did it as a single project. So it should, as I mentioned, be divided by scenes. Let's move on to the demonstration video. And you can see in the upper left part is the original 16mm. In the upper right part is the 35mm internegative. And at the bottom is the machine learning result. I would say it is more or less on track, but a bit more training is needed to avoid those noise issues that sometimes appear. In the previous example, we matched chroma, and in this example, we're copying luma, if you want to think of it that way. Now we move on to the most complex and final example, which is the recovery of references with analog video. Recovery is possible using an analog digital video source like a telecine. The process usually requires many steps to recover the film's complete frame. And the first model, for example, is trained with the less damaged parts of the film to capture special features that are not contaminated. For instance, in the year, you'll see it. The results of this model inform a second model for the recovery of a complete frame. And direct recovery from telecine, as I've mentioned, is not feasible due to cropping and limited spatial information. What do I mean by this? Let's take a look. First, let's start with, I think we should start with this one, yeah? If I show you the original, it's a film that has suffered, that has many damages. It has Rolex damage, it has damage from, has warping, well, parts are breaking away from the film. I mean, it's a very damaged film. Any traditional restoration process would be impossible or almost impossible because the image is so damaged. The advantage we have with this telecine, which was made close to the film's creation, obviously has the classic telecine damage. It has a bit of compression. The telecine was not done correctly. So it has a bit of interlacing, as it's called. Still has interlacing effects, apart from having a moving mask. And, well, obviously the loss of brightness throughout. And the most important thing, which is the cropping. But we can choose parts of the image. For example, we have the original here and the telecine here. We can select parts of the image that are more or less clean from the 16 millimeters, whether partial or complete. To tell the telecine to learn the definition, to learn to recover spatial details, for instance, in the hair, eyes, jacket, or whatever it may be. So we are going to create this first model that will go from here, from the telecine to an, for example, an approximation of what 16 millimeters would be, which I would say is satisfactory. Nonetheless, given the amount of damage, it's really satisfactory. The only problem is that using the telecine as a base involves having problems with two of those incomplete frames because it's video. Now we can go to the other side. We can do literally the reverse. We can go from the 16 and train it with the telecine to have a full clean image, but at a much lower resolution that works. If we compare, obviously the damage seems to be removed, but the image feels much softer, almost like it has lost definition, which might work in a viewing environment, but we couldn't call it completely satisfactory. Then, for example, we can do something like, I have another example that we can create. We can use this model that we've created from the telecine with the 16 that is more or less clean, and use it as a basis to create a model that help give the full characteristics of that to the 16, which is much more satisfactory than going directly from the 16 to the telecine. And it gives us the possibility to recover the full frame. For example, if we look here, this is the original 16 millimeter, and this is the version that has been attempted to restore. Yes, you can really tell as if that layer of dirt or that layer of damage has been removed. Let's watch it. The finished example. In the upper left is the original 16 millimeter. In the upper right is the telecine. On the left is the machine learning going from telecine to 16 millimeter. And in the lower right is the machine learning going from 16 millimeter to telecine. And to finish, an important thing I wanted to tell you is that it is essential to support the use of machine learning models that run locally. That's a picture of my server, and they should be trained with ethically sourced data, meaning our own data or data that has the necessary permissions. Thank you very much.